Okay, good morning, everyone. I want to welcome you to another statistical learning class. And of course, the focus today is on regularization. Okay, but I'm going to have a very quick recap. Okay, coming into this particular topic. Of course, everything started by trying to characterize relationship among variables. And of course, uh, we normally start with module specification. And from module specification, before we specified our module, of course, we four of us started by having what we call exploratory data analysis, trying to understand our data, trying to um, construct a scatter plot matrix for us to be able to know um, whether linear relationship actually occur. And after we are done with the model specification, we go into model estimation. The model estimation can be done either by ordinary least squared or by method of maximum likelihood. And after the model estimation, the next on the line is model validation. Of course, in model validation, you normally want to subject your model to diagnostic testing. Now, the diagnostic testing we're talking about is you're trying to investigate whether assumptions underlying the use of linear regression hold. And what are these assumptions I'm talking about? Talking about assumptions of linearity, assumptions of constant variance, assumptions of normality, also talking about absence of multicollinearity, absence of outliers and high leverage, and so on, like that. I think I've walked you through how you can conduct regression diagnostics. And if there's a problem, if the problem is due to outlier, oh, sorry, if the problem is due to maybe uh, linearity or constant variance, assumptions violated, of course, you can actually make an attempt transforming your response variable. And I remember I walk you through how to transform response variable using what I call a boss cause transformation. Okay. Now, you can only resolve it to that if assumptions are violated. And I also remember before I walk you through how to, investigate the goodness of fit. Okay, the goodness of fit and inference, how you can actually, test, conduct a t-test on individual predator, in a model, and how you can also conduct both F-tests and partial F-tests, in an attempt to investigate model adequacy. And I think I also walk you through how to investigate assumptions of multicollinearity. Okay, the assumptions of multicollinearity can actually, when multicollinearity is present in your model, needs to be fixed, because I told you the consequences of that the other time. And one of the ways to know is to obtain the VIF. If you look at the ongoing assignment, the assignment I released yesterday, so I asked you to obtain the VIF of each of the predator. And of course, a particular predator will be problematic if it is greater than, if the VIF is greater than 5. Okay. And after that, I walk you through what I call model selection. Okay, model selection. I remember I walk you through three different types of model selection. Okay, the first one was off subset selection. The second one was a forward, selection, and the last one was a backward elimination. And of course, why are we in, what we want to do today? So what is the focus, and why do we need to do regularization despite all of that? we've considered every approach, that will make our model to be in a very good statistical standing. So what is what do we need to do again? What have we not done? But let me tell you this. We can never get tired of improving model performance. If there's any way we can have our model improved upon, okay, it should be a welcome development. And that is the reason, you know, I actually want to identify some problem with model selection criteria that we did before, like the up-source selection, the stepwise, regression, the forward and the backward. All of that rely on some rely on p-value in selecting predators, also rely on AIC. Okay. Now, when our approach relies on p-value and relies on AIC in selecting predators into a model, that approach may be prone to overfitting. I'm going to say that again. When you have an approach, okay, that is actually select predators into a model. When I say predator, I mean explanatory variable into a model. Okay, if you base your approach, because the model selection approach that we did last week can also we can use AIC to select predator. Okay, because imagine I fit different kind of models, and I want to there's some models add some predator, some have fewer, some have maybe some predators. Now, what is going to happen? I can use an AIC to select. The AIC is, I'm going to choose the model with the smallest AIC. When I'm using either AIC, BIC, or I'm using a p-value to select predators into my model, then my model could be prone to overfitting. Okay, so in order to get out of the overfitting, okay, and one of the way to get out of overfitting is considering regularization technique. Okay, so and what we mean by overfitting is actually saying that your model will be highly sensitive to small change, okay, in the data. When you have a small change in the data, your model will be highly sensitive to that. And if your model is sensitive to small change in data, then your model will have a issue with generalization. Your model will perform greatly on training data, but it's going to perform woefully or poorly on unseen data. Okay, because of the fact that it is being prone to overfitting. And not only that, I also want to tell you this, the approach of method of selection that I walked you through last time, I mean the off-source selection, the forward and the backward may not be able to control the problem of multicollinearity. I'm going to say that again. That approach of method of selection, the like off-source set selection, the forward and the backward will not be able to control for multicollinearity. Let me tell you this, multicollinearity is one of the major issue in modeling. Okay, I may not be able to control for that. And that is why I present to you LASSO and REACH. And let me also tell you this, one of the weaknesses of the model selection technique that we did the other time, situation where the number of explanatory variables is more than the number of observation, then that approach is no longer going to be efficient. And that is why, because when P is greater than N, in a multivariate setting, there's possibility the numbers of explanatory variables greater than the numbers of observation, that is high dimensional data. Okay, in high dimensional data, that approach will struggle. And that is the reason why we actually need a brand new technique that will come in form of a regularization. Okay, and that is why we want to talk about the LASSO and the REACH. So statistics is like a story that goes on and on and on. And that was why, if you take a look at what I said here, I said, so far, we have seen how to fit linear regression model, which contain a subset of possible predictors. Of course, we've done that. And of course, in this particular lecture, you also see how to construct linear model, which contain all the p possible predictors, but the estimation procedure used is such that some of their respective parameters we're actually going to be shrink. Okay, we're going to shrink towards them towards zero. Okay, we're going to have an approach here that will completely eliminate them. We're also going to have an approach here that will not completely eliminate them, but that will reduce their effects. Even if there's a problem of multicollinearity, the effect will be reduced. So we have an approach here that will actually do that. Now, the lasso regression will shrink, okay, unimportant predictor to zero, thereby eliminating them completely from the model, which means the lasso regression perform a function of feature selection. Okay, but when you take a look at the ridge is still going to retain them in the model, except that they are no longer going to be significant. So ridge, on the other hand, does not perform model selection, step, but ridge, on the other hand, was able to retain some variables in the model because those variables may be relevant, even though they are not necessarily significant. Does that make sense? Okay. Now, so that is that. Now, I'm going to start with ridge regression, and I really want you to see the relationship or the between the conventional regression that we did before, that we call ordinary least square regression. Okay, we want to compare, what do we introduce into Gauss-Markov model of, of the conventional regression. Now, the whole thing started from here. I told you, the whole thing actually, this is the specification, equation one here, is a specification of linear regression model. Okay, now, what we did the other time, we use our least square approach. Okay, the least square approach minimizes the residual sum of squared. Okay, and by that we're able to have parameter estimate. Okay, but in the case of, if I actually believe that in this model there's something, I actually need to introduce a penalty. I need to introduce a technique, a term that is actually going to address, some irrelevant variables that may be problematic to this. So what I'm actually going to do is I'm actually going to attack the residual sum of squared. I'm going to attack the residual sum of squared and added a penalty. Now, this is the model, okay? This is the model, and if you take a look at what I have now, take a look at this. That is the penalty that I'm actually adding, okay? The conventional model has a residual sum of squared. The residual sum of square is this. The residual sum of square is the difference between predicted, okay? The sum of squared of the difference between the predicted and the actual. You know what I mean? Predicted response, the actual response minus predicted response. You remember Y minus Y cap, okay? Y minus Y cap is residual. But you know what? If I square that, if I square residual, and I sum the residual, okay, where this one is I sum it over observation n. Okay, if I sum it over observation n, okay, then I have residual sum of squared. Okay, don't forget the Y cap is the estimated model. The Y cap, okay, the Y cap is actually equal to X beta cap. I think you know that. And that is exactly what you are seeing here. Okay. Now, what are we trying to do? We want to minimize this. Okay. We're still minimizing RSS, but we have incorporated, okay, we have incorporated a regularization term. Okay. Now, if you take a look at the regularization term here, okay, it is just what we are adding is the square, the sum of square of the regression parameter. That's what we're adding. That's what range is adding. Okay, which means the range here is actually going to increase the bias, but the variance is going to go down. Don't forget, what are we trying to solve? We're trying to solve a problem of overfitting. Overfitting, what lead to overfitting is high variance. I'm going to say that again. What led to overfitting is high variance. So the idea behind regularization is, can we have a way to minimize the high variance? But when you are minimizing high variance, you're also increasing bias. That's okay. Okay. So that is what you're saying. And the lambda here is the turning parameter. Okay. Is the one that determines the strength of this regularization. The strength of the regularization. Okay. Now, at the end of the day, okay, we're now going to have, if you take a look at this now, that is the ridge regression estimate. If I want to get ridge regression estimate from data set, that's what I'm going to use. Do you know that when lambda equal to 0, when lambda equal to 0, this is going to break down to the conventional OLS estimate. The OLS estimate, do you remember what we derived the other time? The OLS estimate is just going to be X prime X inverse inverse X prime Y. Look at that. Okay, when lambda here equal to 0, okay, that is what it's going to become. So the lambda is the turning parameter. Okay, now I actually want to move right now. Still talking about range. Now, if lambda equal to 0, you know, we condition, we have a constraint. If you take a look at the constraint here, we believe that we are introducing this guy, okay, summation lambda j squared, and that lambda j squared is less or equal to a particular term, and that term is positive. Look at that, it's non-negative. Okay, it's non-negative. Now, if I want to understand the behavior of lambda, when lambda equal to 0, I told you the other time, I said the ridge regression estimate will become the OLS. Now, when your lambda is 0, you know what it's telling you? You don't need regularization. You need to, you can still pursue, the regression using the OLS, using the least square approach. That's what it's telling you. Okay, which means when lambda equal to 0, it's trying to tell you the penalty introduced has no effect. But as the lambda is becoming large, okay, don't forget, when lambda is becoming large, that S is going to becoming 0. When lambda is becoming large, then the ridge regression, we get closer and closer to 0. But it's just not going to be 0. It's going to, don't forget, I told you, the ridge regression, is will not completely eliminate the predators, the irrelevant predators. Irrelevant predator will still going to be in your model, because let me tell you this. What you call irrelevant predictions may be very good for prediction, even though irrelevant predator may not be good for explanation. Does that make sense? Irrelevant predator may not be good for explanation, but they could be good for prediction. So I told you the other time, we have different kind of intention in statistics. Okay, explaining is different from predicting. Okay, that's exactly what I'm trying to say. So the moment you shrink that to 0, then it means the penalty will have a larger effect. So Now, I just trying to tell you when lambda is close to zero, when lambda is exactly zero, the ridge regression estimate become the OLS estimate. And when lambda is tending to infinity, is becoming extremely large, then we expect the ridge regression estimate to be moving closer to zero. But they are never going to be completely eliminated. It's still going to retain them. Okay, now I want to go into an example now. Okay, we consider the data set credit from the Arrow package ISLR. If you want to have access to this data, you can load a package now. We got some data set that are inbuilt in our, okay, and we collect for 10,000 individuals, okay, over this particular variable. You can see ID, income, limit, rating, card, age, education, gender, ethnicity, balance. But let me tell you this, whenever I give you assignment or exam, I'm actually going to tell you what your response variable is. I remember in the ongoing assignment, I gave you the data set on rate my professor data set. Of course, I said the response variable is quality. Okay, here the response variable is balance. Okay, balance, which is average credit card balance in United States dollars. Okay, now this is the first six of the data frame. Okay, this is the first six of the data frame. Now, the data frame actually come with categorical variable, gender. You can see gender, whether you are a student or not, whether you are married or not, or what about the ethnicity? Okay, I need you to pay attention. This is a mixture of categorical and quantitative variables. And when you are dealing with a quality, categorical variables don't fall into domain variable trap. Okay, so now, and that is why here I said for gender, you are actually going to use one dummy. For two categories, don't forget K minus one number of dummy. And for three categories, it's going to be two dummies that you're actually going to use. So we're just saying that as an example. So how do we include a categorical variable with levels into our model? Okay, the number of categories minus one. Okay, I told you the other time. Okay, now I wanted to look at this. What am I actually displaying? Okay, you know, I'm trying to compare the parameter estimation. We have already estimated, for instance, you estimated the regression parameter based on rating on students, whether the person is a student or not, the income and so on like that. And I need you to pay attention here. Oh my God, what is happening here? As the lambda is increasing, they are kind of shrinking toward zero when the regression coefficient associated with predator, is moving toward zero, is actually confirming their irrelevance in the model. But they are not going to be completely eliminated, okay, by ridge regression. I just wanted to take note of that. Also, I said, yeah, conversely from the LSC estimate, the ridge estimate are not scale invariant. This means that if we change the scale of SJ, the estimate of BJ will change substantially, and not just by a scaling factor, as the covariance should be standardized before being included. Now, let me tell you this. Before you can use the idea of regularization, you need standardization. Of course, we do that most of the time, because different variable may have different scale. We don't want one variable to dominate. It's just like before you start a case in a court, judge is already taking a side. That's not good. That's what we mean here. We actually want to bring them into the same scale. Does that make sense? Okay, so that is exactly what I'm trying to talk about here. So if I have this guy here, and if we rescale instead of X, and we're doing AS, at the end of the day, you're actually going to see that that is different from beta cap. It's 1A beta cap. And that's why that needs to be rescaled. That needs to be standardized. Okay, we don't want something that will actually affect the result. Okay, now I need you to pay attention. Take a look at this. When you have a small lambda, you know, you could have a small values of lambda that I call tuning parameter, and we have a large values of it. Here I said, model which are very flexible, have low bias, but high variance. You know, they are flexible. You know what make them flexible? Because they got so many parameters. They got so many predators. And that could be noisy. Even though they have low bias, they could be noisy. If it is noisy, what do I mean? This is noisy. Let me write that. Noisy. Noise. It could be noisy. Okay. If it is noisy, then that will overfit. That means there's going to be high variance. Okay. And that is what we mean. So the small lambda, okay. So I just wanted to take note of that. But model, what about model with less flexibility? Okay. Model that are less flexible, okay, have large bias, but low variance. Okay. Let me tell you this. In statistics, the problem of statistician, the problem of everyone in scientific community is bias. Okay. They want to run away from large bias by trying to, incorporate so many predators into the model. If you have so many predators in your model, there's possibilities. Some may be giving the same statistical information, or some may not even be relevant. Okay, and that is why the role the lambda play here, the tuning parameter play here is a variance bias trade-off. That is the role the tuning parameter is actually playing. Now I have another example here. Okay, an illustrative example. We consider a simulated data set with P equal to 45 predators and N equal to 50 observations. Okay, and we want to implement ridge regression considering different values of lambda. And for each value, consider we compute the square bias. We compute the square bias, and of course, we are the variance. So the square bias in black, the variance in green, and the test mean square error. So take a look at this. Of course, because don't forget, you're going to split your data. Don't forget, you're going to split your data to training and test set. And that is the reason why you are eventually going to compute the mean square error for the test. Okay, data. Now, we are testing the effects of, of varying degree of lambda, which is the tuning parameter. Okay, if you take a look at this now, the gray one, the variance. Okay, the black one is the bias. That's exactly what we talk about here. The square bias. But that bias could be negative or positive. We normally consider square bias. Does that make sense? Okay. Now, if you take a look at what we have here, give me 1 second. I think I'm gonna clean up. Okay, gonna clean up that. Let me see if there's any other one that I need to clean up. 1 second. Okay, I also need to clean up that guy. Okay. Okay, now I'm gonna go into this now. Take a look at this now. Now, what you have here is a mean square error. It's like we want to know what is the optimal values of lambda that is going to work. Don't forget it, lambda here, the tuning parameter is the one that determines the strength of this regularization. Okay, we want to know from the data set, the one that's actually going to work. Okay, now I said here, all the parameters are allowed to be far from zero. Okay, if all the parameters are allowed to be far from zero, okay, then it means the model is going to be more flexible. Far from zero, you have so many parameters, you have so many predators, okay, will be more flexible. But in a situation where more parameters are set close to zero, then the model become less flexible, okay? Less flexibility, okay, is what you are actually, what I'm talking about now. So the question now is, what am I going to do? Do I want to set them to be very close to zero or far from zero? What we normally want is an optimal values of the turning parameter. Now, if you take a look at what I'm displaying right now, you actually gonna see. Now, you see, I talk about the bias, I talk about the variance, I talk about the test MSE. Now, according to Rao-Blackwell theorem, you remember that the mean square error, the mean square error of an estimator. Can somebody remind me of the formula for extra credit? If I want to write the mean square error of an estimator in terms of variance and bias, what is it going to be equal to? Somebody tell me. The mean square of an estimator. What is it going to be equal to if I want to write it in terms of variance and the bias? It's going to be equal to variance, the variance of an estimator, plus the square of bias. That's what we call mean square error, plus the square of bias. What happened when bias is zero? The mean square error of an estimator equal the variance of an estimator. That is when bias equal to zero. You can see here, I'm talking about variance. I'm talking about bias squared. When I add the two together, that gives me mean square error. Does that make sense? Now, I said, given what we've discussed before, are these results surprising? This result is not surprising going by theoretical provision as given by our Blackwell theorem. And not only that, I said no, because of the bias variance trade-off, we expect to have the minimum of the test MSE when the model is neither too flexible or little flexible. Now, let me tell you what we want. We don't want our model to be more flexible. We don't also want it to be less flexible. So that is why we want to strike a balance. Okay. And that is why we say we have a good balance. We'll be able to have a good balance between the bias and the variance. It's like somebody trying to stand in the middle. Does that make sense? Okay. Now, we've talked about ridge regression. Okay. We have the advantages of ridge regression. Okay. We have disadvantages. Okay. Now, I said it allows to select between more flexible and less flexible models. You see that? And it is computationally more efficient than the LSC, because the LSC, using this best subset selection, you're actually going to go through all models. And let me tell you this, ridge regression does not perform variable selection, because you're still going to have all predators in your model, except that irrelevant one will not be statistically significant. Does that make sense? And that was why I said it includes all the predators in the data set. Because having some predators in the data set, even though we said they are not statistically significant, they could improve predictive accuracy of a model. Okay? And if P greater than N, it performs well. In fact, when the number of observation is less than the number of explanatory variable, the OLS, the least square method, is going to break down. Okay? It's going to break down. But you know what? The ridge regression is still going to perform excellently well, even in high dimensional case. But what are the advantages? I showed the other time. Standardization needs to be done before using ridge because the estimates are not scale invariant. Okay? Now, the estimate can be very close to zero, not exactly zero, and thus they may be hard to interpret because you still have a lot of variables in your model. When you have a lot of predictors in your model, but particularly if they are correlating, okay, it will cause issue of interpretation. It's going to cause an interpretation issue. But if you are succeeded in eliminating them, okay, that will actually enhance interpretability. Okay, now because of this, we move into lasso regression. You know, if you look at equation 3, what lasso is adding, what is adding is the absolute value of the regression parameter. But what ridge is adding is the square of the regression parameter. Okay, now we actually this lasso actually uses what I call L1 penalty, L1, but ridge uses L2 penalty. Okay, so I just wanted to take notes of that, and that was why I said here that okay, I think I said that. And the advantage of using L1 penalty over L2 penalty is that it will shrink that regression coefficient to zero. Well, when it shrink the regression coefficient to zero, you know what is going to happen? Then the irrelevant predictors will be completely eliminated from the model. So because of that, lasso regression perform, feature selection. Does that make sense? Okay. Now, take a look at this. It's shrinking them to zero. You see what I have now? It's shrinking them to zero. If they take a look at this, all of them towards, you see that zero? Shrinking all of that to zero. All variables that are not that important. When lambda becomes large, you can see this here is talking about lambda. Okay, when lambda is large, it's going to eventually shrink all of that to zero, and it completely eliminate them. Okay, now I said, what are the main differences you see with respect to the ridge? Okay, this is what I'm saying. Comparing this guy with uh with this guy. Okay, this is around zero, around zero. Okay, it's for the ridge is around zero, but for the lasso, okay, it's going down to zero all the way. You see that? That is the difference. Okay, and that's what I said here. I said in ridge regression, the coefficient are never set exactly equal to zero, whereas lasso we set many of them exactly equal to zero. Okay, and I said the covariates such as rating, which are quite important in predicting our outcome balance, are kept away, from zero until ladder get very large. There are some variable, even though they may not have statistical significant effect, but practically they should be in our model. In that situation, the appropriate regularization should be reached. Okay. Now, I said Lasso enjoys similar advantages and disadvantages than Ridge, but it also leads to more interpretable results. Why do you think Lasso lead to more interpretable results? Because we have few more predators. He has already eliminated the irrelevant one. Okay, so and that was why as I said, some of the coefficients are estimated equal to zero. Thus, we may expect Lasso to perform better than Ridge, when the true underlying model is sparse. Okay, sparse, like sparsity. Okay, because maybe your intention is, oh, I got a lot of variables. Okay, and I actually want to sparse my model. Sparsing a model is eliminating some completely that are not relevant. So that's why I said most of the predictors that are not related to the response. And I said this. However, this may not necessarily be the case if most of the predictors are related to the response. You know, predator may be related to the response. Okay, they may not be statistically significant, but we may still need to have them in the model. Okay, so based on the examples, again, I wanted to see the one. Now let's take a look at this. You happen to be a researcher, you perform reach, right? You have that, okay, and you perform lasso, okay, and you have another one. Now the question now is, out of the reach and lasso, okay, which one do we actually are you likely going to recommend? For both, you have test MSC. Of course, what is going to happen is for you to be able to take a decision is going to depend on your intention. Do you want to predict or you want to explain? Please pay attention to choose between using the reach and, you know, using the lasso. Okay, it actually depends. So if you take a look at what I'm showcasing now, okay, if you take a look at what I'm showcasing now, okay, the dot 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 in one module for lasso and the other one for the reach. Now, there's something I also wanted to see here. Okay, in the denominator, you see r squared, and here it is lambda. Okay, and when I look at the test MSC, okay, if I look at the test MSC, I'm actually seeing that they are very more or less the same, both the reach and the lasso. If you take a look at the test MSC, okay, but where different may seem to exist is the variance and the bias. And that was why I said here, okay, I said, which one between lasso and regression will you choose? In this example, I said lasso and reach perform quite similarly. Therefore, one cool, because they perform similarly. How do I know? The test mean square error is kind of very, much if you want to base on this. Okay, the dot 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 is for reach, and the other one is for lasso. You can see they're very close. Okay, and there's something that I said here. If you take a look at this, look at the bias, also very close, but look at the variance. Do you see the variance? You see the dot dot dot. For the variance, the dot 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 is under, right? It's under, and don't forget the mean square error is what we're interested in. Okay, even here, the dot 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 is seen to be under, but very close. Okay, and I said something here. I said, if you choose, I said, if we care about the best possible prediction, we have to choose reach. Best possible prediction, don't forget, reach will not shrink all the predator to the regression to zero. And I told you the other time, that is good for our prediction. Having so many predators in our model is good for our prediction. May not be good for our model explanation, but good for the prediction. And I said for lasso, if we want to interpret, okay, if our focus is model explanation, interpretation, we actually need lasso. Lasso is going to be a better choice. Okay, lasso is going to be a better choice. Okay, for interpretation, but lasso is not going to be a better choice for prediction. Okay, based on what we actually see now, based on what we see now. Okay, now let me tell you this, the most issue, okay, in conducting in lasso and the range is how do we figure out the turning parameter lambda, okay? And that's what I write, selecting the turning parameter lambda. Because we want to select the turning parameter lambda that will minimize, not only that will minimize all of this, both the residual sum of squared and the penalty time for lasso and for for range. Okay, and this is what we can do. We can do this by way of simulation. Thank God, the other time we've already done how we can validate. We can start by dividing our data set into training and and validation sets. Then we can define a grid of positive values for lambda that will range from a very small values of lambda to a very large value. Does that make sense? And that's exactly what I'm defining here. Now, for each of the value of lambda, you know what we're going to do? Then we're actually going to fit reach over the training set. Okay, you can see all of that. You see what we're fitting now? For each parameter value for each lambda value, we're fitting all of that. Any question on that? Okay, we're assuming different value for lambda we fit. Then in the validation, then we're also going to have our validation. Then we're going to have the mean square error. What are we looking for? The value of the lambda with the smallest mean square error is what we're going to choose at the end of the day. Does that make sense? And that was what I said. Choose lambda for which MSE is the smallest. Okay? We have to choose lambda, the turning parameter, which is the strength of the regularization technique. Okay? Now, this is how you can actually plot that if you take a graphically for you to see. Okay? Now, when lambda increases, don't forget, when lambda increases, the model becomes less flexible. Okay, whether you are talking about reach or lasso, but more interpretable in lasso. But lasso we shrink that to 0. Okay, so take a look at this. When lambda increases, bias increases, then the variance decreases. Don't forget, okay, we had problem of overfitting. Overfitting was caused by high variance. We're making an attempt to reduce the variance, but in the process, in a way, we're actually going to increase bias too. But we can have a trade-off. We can balance that. Okay, now let me now tell you this. Finally today, reach as an issue. Range regression as an issue. Lasso also as an issue. Let me tell you the issue with reach. Reach was not able to shrink the regression parameter to 0, still retain them. There's still possibility. We still have little noisy in a way. Why? What is it called? Lasso, on the other hand, shrink them to 0, eliminate some features that may be good for prediction. Now, how do we actually strike a balance between the reach and the lasso? Then we can have a new model, okay, that will combine both reach and lasso. Look at that. This is the residual sum of squared. We are having parameter for reach. We are having parameter for lasso, but we're going to introduce what I call a transition parameter, alpha. When alpha equal to 0, okay, when alpha equal to 0, it's going to be lasso. When alpha equal to 1, it's going to be reach. So definitely our alpha now is now going to be between 0 and 1. So that we want to have some sense of reach. We also want to have some sense of a lasso in our model. And that is what we call elastic net regression. Okay? That's exactly what I put here. Is there any question before I go today? Is there any question? That's our next topic. Now, let me tell you this. I quickly want to talk about the midterm. I will release a practice question for midtime on Wednesday. And of course, what you should be expecting, you should focus on everything that we have done up to today's Monday. What we're going to start on Wednesday is never going to be part of midtime. Does that make sense? Okay, this is where I'm going to stop. Make sure you all stay safe and have a lovely day. Bye for now, everyone.